Greetings and welcome to the 12th episode of PHS Physics SOS. Today I'm going to be going over the homework from section 5.3, which covers more stuff on work and energy, starting with question 4 on page 193. Now question 4 reads, a pendulum swings back and forth as shown in figure 5-18. Does the tension force in the string do work on the pendulum bob? And does the force of gravity do work on the pendulum bob? Explain your answers. So first we're going to draw a little diagram of a pendulum. So if the pendulum is at the bottom of its arc, so here's the top, here's the string, and here's the little pendulum bob on the bottom. So the tension in the string is pulling it this way, upwards, but the motion of the pendulum at this point is to the right, which makes a right angle. So since the force is perpendicular to the motion, it means that there is no work being done by the tension on the bob, because work is equal to force times distance times the cosine of the angle between the two vectors. So in this case, work is equal to force times distance times the cosine of 90 degrees, which is, if you plug it into your calculator, 0. So the work is going to be 0 no matter what the force and the distance are. Now, even if you look at it, say, up here, the tension's at a different angle. The tension's going this way as opposed to this way. But now the pendulum is going this way, which is still at a right angle. And even over here, same story. No matter which way it's going, the tension is always, no matter where it is in its arc, the tension is always going to be at a right angle to the motion, meaning the work done by the string on the pendulum is going to be 0. Now the next part asks if the gravity does work on the pendulum. Now, if we look at the gravity, say up here, I'll redraw this. The gravity is acting this way. Now if we split this up, we get this and this. Now this vector, again, is perpendicular to the motion of the pendulum because the pendulum is moving this way. So this component of the gravity is not doing any work because it's at a right angle, meaning the cosine of that angle is 90 degrees, meaning the cosine of that angle is 0, meaning the work done is 0. But this component of the gravity is doing work because it's in the direction of the motion. So the answer is yes, the gravity does do work. So the answer is yes, the gravity does work, but no, the tension does not do work. The next question is question 5, which reads, the drivers of two identical cars heading towards each other apply the brakes at the same instant. The skid marks of one of the cars are twice as long as the skid marks of the other vehicle. Assuming the brakes of both cars apply the same force, what conclusion can you draw about the motion of the cars? Okay, so what they're saying is two cars were heading towards each other. Now, the skid marks on this car are going to be, say, that long. And the skid marks on this car are going to be, say, that long. So we'll call this 10 meters. Call this 20 meters. So, they said both cars were identical. So we'll say this was, and the forces of the brakes were identical. So we'll say that the mass was equal to, and we'll call this car 1 and car 2. So the mass is equal to 1,000 kilograms. I'm just making this up, just for example, because you can still do the math, even if as long as your numbers satisfy what the problem gave, as far as conditions. So we're going to give the mass of 1,000 kilograms and a force, an applied force of 1,000 newtons. So we know that this car stopped in 10 meters, and this car stopped in 20 meters. So to figure out the amount of work done in that distance, I'm going to go work for car 1 is equal to force times distance, and work for car 2 is equal to force times distance. So both the forces are 1,000 newtons, but they have different distances. So the work for car 1 is equal to 20,000 newtons. And the work for car 2 is equal to 10,000 newtons. What this means is it took this much energy, 20,000 and 10,000 joules respectively for each car, to bring them to a stop over this distance from their initial velocity to their final velocity of 0. And using these energies, I mean, intuitively we know that longer skid marks means faster initial velocity, shorter skid marks means slower initial velocity, which is all the question is asking, but I'm trying to prove it mathematically so you can understand the concept better. So now, if we set these equal to the initial kinetic energy, then we can solve for the initial velocity. So 1/2 mv squared equals 20,000, which means mv squared equals 40,000. Our m is 1,000, so our v squared equals 40, and v is equal to about 6.3 meters per second. So that means, at this point, this guy was going 6.3 meters per second, which means he had an initial kinetic energy of 20,000 joules. And now over 20 meters, applying a force of 1,000 newtons from his brakes, he came to a velocity of 0. Whereas this car started off with a kinetic energy of 10,000 joules, which means he had an initial velocity of 4.5 meters per second. So, even though we didn't need to do all this math, conceptually it makes sense, again, that longer skid marks means they were going faster in the beginning, and shorter skid marks means he wasn't going as faster in the beginning. But now, using work and energy, we can prove why that is. The next question is question 8, which reads, a flight attendant pulls her 70.0 Newton bag a distance of 243 meters along a level airport floor at a constant speed. The force she exerts is 40.0 newtons at an angle of 52.0 degrees above the horizontal. Find the following. A, the work she does on the flight bag. So, remember, work is force times distance, but it is only in the direction of the motion. It is only that component of the force that's in the direction of the motion. So if here's our bag and she's pulling with 40 newtons at an angle of 52.0 degrees, then if we do a little trig, you can find that this side is equal to 24.6 newtons, and this is in the direction that the bag is going. So in this case, this is going to be equal to not 40 newtons, but 24.6 newtons times the distance that the bag traveled in that direction. Because the bag's going this direction, and 24.6 newtons of this force is in that direction. So this is times 253. And if you plug that into your calculator, you should get 6,230 joules. Part B says the work done by the force of friction on the flight bag. Now, it says in the problem that she pulls it at a constant speed, meaning that the force of friction and the applied force are equal to each other. So, the force of friction pulling backwards is also equal to 24.6 newtons. So, the work done by friction is going to be equal to 24.6 newtons times the direction it's going in, times the distance traveled, which is also equal to 6,230 joules. However, since the bag is moving in this direction and the force of friction opposes that motion, the work done by the friction is negative because it's in the opposite direction of the motion. If the force doing the work is in the opposite direction of the motion, then the work done is going to be negative. Remember that. And part C says it wants to know the coefficient of kinetic friction between the flight bag and the floor. So the only equation we know that has a coefficient of kinetic friction is F equals mu times normal force. So the force of friction we know is 24.6 equals mu. But what's our normal force? Immediately, you'd be inclined to think it's 70.0 newtons because that's the weight of the bag. But if you look up at this free body diagram, you'll realize that the flight attendant is actually providing 31.5 newtons in the upward direction. Because if you split up her force, it's 40 newtons at an angle, which splits up to 24.6 horizontally and 31.5 vertically, which means that the ground, the normal force provided by the floor, is actually 70 minus 31.5, because the flight attendant is providing these 31.5 newtons of upward force, so the floor only has to provide 38.5 newtons of upward force, which is equal to our normal force. So back into this, we have our force of 24.6 is equal to mu times our normal force of 38.5 newtons. And if we divide these over, we get 24.6 over 38.5, which is equal to mu, which is equal to 0.639. And again, it's a coefficient of friction, so there are no units. And the book actually has the wrong answer for this, so yeah, don't trust the book. The next question is question 12, which says, can the kinetic energy of an object be negative? And the answer is no, and here's why. So we know that kinetic energy is equal to 1/2 of mass times our velocity squared. In order for the kinetic energy to be negative, one of these components has to be has to be negative. So the mass to be negative, well, we know that can never happen, because your mass is an absolute quantity. It cannot be less than 0. But for the velocity, for the square of the velocity to be negative, then it wouldn't really work, because if v squared was equal to, say, -10, then the square root of -10 would be not a real number, and in physics we're only working with real numbers. So, because velocity would then be an imaginary number, which, yeah, we don't work with. So since both of these quantities are always going to be positive, kinetic energy cannot be negative. While you can have a negative velocity, like say your velocity is equal to -5, then your velocity squared is still going to be positive, just because of how multiplication works. So your kinetic energy can never be negative. So it cannot be less than 0. The next question is question 20, which reads, a spring has a force constant of 500.0 newtons per meter. Show that the energy stored in the spring is as follows. And part A says 0.400 joules when the spring is stretched 4.0 centimeters from equilibrium. Ugh. Okay, again, we have to convert units, which is just obnoxious at this point. So first thing we're going to do is 4.00 centimeters is equal to 0.04 meters. So to calculate the amount of energy stored in a spring, given a spring constant and a distance, you just have to use the formula U sub E, elastic potential energy in a spring, is equal to 1/2 kx squared, where k is your spring constant and x is the displacement of the spring. So it's going to be equal to 1/2 of k, which is 500, times 0.04 squared. And if you plug that into your calculator, you should indeed get 0.400 joules, which is what they were looking for. Part B says 0.225 joules when the spring is compressed 3.0 centimeters from equilibrium. Again, 3 centimeters equals 0.03 meters. So your elastic potential energy at that distance is going to be 1/2 of 500 times 0.03 squared, which if you plug that in, gives you exactly 0.225 joules. Now part C says to prove that it is 0 when the spring is unstretched. Okay, now to do this, use the same equation, but you just plug in 0 for x. Now when you have 0 multiplied by anything else, the quantity is going to be equal to 0. So you have 0 joules when there's 0 joules of elastic potential when it's at its resting position. The next question is question 23, which says, a ball is thrown straight up. At what position is its kinetic energy at a maximum? And at what position is its gravitational potential energy at a maximum? So let's look at what gravitational potential energy is and what kinetic potential energy is first. So gravitational is mgh, and kinetic is 1/2 mv squared. So as a ball is thrown up and comes back down, what's varying in these two equations? Well, we know that the mass is constant, so it's not those. We know the gravity is constant, so it's not that. 1/2 is a constant, so it's not that. So what's varying for gravitational potential is the height, and what's varying for kinetic energy is the velocity. So to maximize gravitational potential, we want the greatest height, which is at the top. And to maximize kinetic, we want the greatest velocity, which is either at the very bottom when it's thrown or at the very bottom on its way back down. So the potential will be at a maximum. So the potential will be at a maximum when the height is at a maximum, or at the top of the throw, and the kinetic energy will be at a maximum when the velocity is at a minimum, when the velocity is at a maximum at the bottom of the throw. The next question is question 27, which says, a child and a sled with a combined mass of 50.0 kilograms slide down a frictionless hill. Just so you know, frictionless hills don't exist. That'd be absolutely insane. This child would be hauling ass and dead by the time he hit the bottom of the hill. If the sled starts from rest and has a speed of 12.0 meters per second at the bottom, what is the height of the hill? So we know that our mass is 50.0 kilograms, and the final velocity is equal to 12 meters per second. So, and they want to know the height of the hill. So, given that this chapter's on energy, and the only equation that we have that has height in it in this chapter is the potential energy due to gravity is equal to mgh. We have to assume we're using that somewhere. But if we start plugging things in, we get u of g equals 50 times 10 times h. So now we have one equation, but we have two variables, which we can't solve. So now we need to look at other equations in this chapter that we've used that have these variables. So, okay, what else can we look at? We know that at the bottom of the hill, the potential energy due to gravity is equal to m times g times a height of 0. So the potential energy due to gravity is 0. But we also know that the kinetic energy of the kid and the sled are at a maximum. So the kinetic energy is equal to 1/2 50, so 25 times 12 squared, which is equal to 3,600 joules. Now, we know that the sum of the energies of the system have to be the same throughout. So that means at the top, the potential energy due to gravity, so at the top of the hill, the potential energy due to gravity and the kinetic energy have to be equal some constant c. And at the bottom, the potential energy due to gravity plus the kinetic energy has to be equal to that same constant c. Now, at the top, we know the kinetic energy equals 0, and at the bottom, we know that the gravitational potential is equal to 0. The reason the kinetic energy is equal to 0 at the top is because he starts out with 0 velocity. So that means at the top, our gravitational potential is equal to c, and at the bottom, our kinetic energy is equal to c. Now, we just calculated our kinetic energy at the bottom, so now we can calculate our gravitational potential at the top by setting this equal to 3,600 joules. So 3,600 equals 500 times h, and if we divide that out, we get 7.2 meters equals the height of the hill. The next question is question 29, which says a 50.0 kilogram pole vaulter running at 10.0 meters per second vaults over the bar. Assuming the vaulter's horizontal component of velocity over the bar is 1.0 meters per second and disregarding air resistance, how high was the jump? So again, same kind of concept as the last problem, that the potential energy of gravity at the beginning, so initial, plus the initial kinetic energy, has to be equal to the potential energy due to gravity at the end, plus the final kinetic energy. So at the beginning, we're going to assume his height is 0 because he's on the ground. So that means his gravitational potential is 0, because if you plug H into mgh, if you plug H equals 0 into mgh, you get 0. Plus his kinetic energy, which we'll calculate in a second, is equal to his gravitational potential at the top, which is equal to mgh, and this is the h we're looking for, plus our final kinetic energy, which there actually is one, because he says he has a velocity of 1 meters per second when he's moving over the bar. Now, initially, he has a velocity of 10 meters per second, so the initial kinetic energy is going to be equal to 1/2 mv squared, which is equal to 1/2 times 50, which is 25, times v squared, which is 100. So we have an initial kinetic energy of 2,500 joules. This is equal to our final gravitational potential, which is m times g times h. Now we don't know h, but we do know that m is 50 kilograms and g is 10, so this is 500 times h, plus our final kinetic energy, which is 1/2 mv squared. The velocity is 1, mass is 50, so 1/2 50 times 1 squared, so we get 25 joules. So if we subtract our 25 joules over, we're going to get 2475 joules equals 500 H. Now if we divide by 500, we will get H equals 5.0 meters. The final question for this problem set is problem 31, which says a 0.250 kilogram block on a vertical spring with a spring constant of 5.00 times 10 to the third newtons per meter is pushed downwards, compressing the spring 0.100 meters. When released, the block leaves the spring and travels upward vertically. How high does it rise above the point of release? So the first thing we want to do is note that at the beginning, it only has elastic potential energy. That energy then that energy turns completely into kinetic energy, initial kinetic energy. Then that energy turns completely into gravitational potential energy when it's at the peak of its travel. So when it's at the top height, it has no kinetic energy because it has no velocity, and all its energy is gravitational potential. So we can say that our initial elastic potential is equal to our initial kinetic is equal to our final gravitational potential. So, we don't care about initial kinetic. We can just set the initial elastic equal to the final of gravity, because we wouldn't actually be calculating kinetic energy. We'd just be saying, okay, it's equal to this. So this is 1/2 kx squared is equal to mgh. So, I'll bring this over here so we have more room. So 1/2 of 5.00 times 10 to the third, which is 5,000, times x squared, which is 0.1 squared, is equal to mgh. So we know that our mass is 0.250, times gravity, which we're going to say is 10, times our height, which is what we're looking for. And now it's just plug and chug. So this is 2,500 times 0.01 is equal to 2.50 times h. So 25 is equal to 2.50 times h, which means our height is 10 meters. And that's the last problem. Thank you for watching this episode of PHS Physics SOS. I hope you found this useful. If you have any questions about these problem sets or any previous or further homework, please leave questions in the YouTube comments below or on the Facebook group, or you can message me personally on Facebook, text me, Skype me, whatever, and or talk to me at school, and I will do my best to help you. Thank you.